All right, nerds. So we're back, and now we're going to move on to some fairly exciting stuff, some really hands-on stuff, and we're going to stop talking about static electricity, and we're going to start talking about current electricity as we move on to intro to circuits. So we're going to talk about how we get electricity to move around a path. Okay, so what's the point? Basically, by the end of this, we need you to understand the symbols used in drawing a circuit. You need to be able to write them up yourself, draw a circuit, and then in the next lesson we'll play with building them. You also want to be able to explain what a circuit is and what the main components are. Okay. Now you need to remember, electrons hold negative charges, and moving charge is the movement of electrons. So, let's talk about circuits. We've got our little example down here. There's two examples. Maybe we'll just focus on this one here for the sake of easiness. Alright. So basically, a circuit is a pathway that electric current, or moving electricity, can flow around. Okay, so it goes around this way. Boom. Now, while it's flowing, we can convert it into another type of energy. Now, electricity is a type of energy. It's the energy which pushes the electrons around. And now, it's the energy which can be converted. Okay, so each circuit has three aspects. You have the energy source. Now, there can be a couple of things. It can be a battery, a cell, or a battery, which is a collection of cells put together, a transformer, mains, power supply. That's about it, really. But there's a few other things it can be. So you need a supply of energy, a power source. So then we have a connecting path. So in this one here, by the way, where's our mouse? Here's your power source. These wires, that's your connecting path. And then you need a load. Now the load is an energy user. So it's something that converts the electrical energy into another type. For example, globes. We've got the globes here. You can have buzzers, you can have a heater, you can have all sorts of things. But it needs to convert that type of energy into something else, and that uses it up. Now, basically, energy needs to be added into the circuit. So, as it's used, the electrons aren't used up. They'll continue to flow around, but the energy pushing them around, that's used up. And it needs to be continually added to it. So, every time the electrons go around the circuit, they hit the battery, and they're given an extra little push across. And they just keep going and going and going until the battery runs out of energy. Now, this is the law of conservation of energy. If there was absolutely nothing using the energy up, if this was a perfect wire that had no what we call resistance, which is what uses the energy up, and there was no globes, no load in there at all, then yeah, technically the battery should connect, stay powering the electrons around that circuit forever. That won't actually happen because that ideal circuit doesn't exist. And this is the law of conservation of matter, or energy, sorry. So now let's look at our circuit diagrams. Now, circuit diagrams are schematic diagrams. This means they're two-dimensional, they're simplified, and they're representative. They don't look like this. Like, this is a drawing. This is a circuit diagram. So you can see that it doesn't look like this exactly, but we can build this from this set of diagrams. So they use a language that is pictorial and universal, and the sort of / almost is because, well, there are a couple of things where there's differences. For example, the light bulb here, resistor, you see we've got a couple, and we'll see a few as we go. So these are our things that you could have in your circuit right now. Like there are other things that could be added later on, but we'll start off nice and simple. So we've got where's our mouse again? You've got a connecting wire, a switch, you've got an ammeter which we use to measure the current, a voltmeter which we use to measure the power. So the ammeter is how many charges are moving past. The voltmeter is how much energy they have, how much push there is. There's a resistor, which is just something that uses up the energy, and they're actually quite useful. There's an electric motor, there's the battery, and there's the light bulb. And if you see the light bulb, you see it doesn't really look anything like a light bulb, but that's actually quite useful, and that's the way we draw them. All right. Now, one thing before we finish up. You need to draw those. Conventional current. Okay, so This is science going, when I was a kid, things were better, and it's not. But electrons actually flow from negative to positive. You remember we talk about field lines, we say field lines go from positive to negative? Well, because of opposites attract, the electrons actually run from negative, because they are negative, to the positive source. Now, that's the way electrical current actually moves, but we use conventional current. Now, conventional current is just the way we draw electron flow. We draw the flow of current. Now, current moves around so fast that it doesn't make a difference anyway, but the current is actually traveling from negative to positive, but conventional current is traveling from positive to negative, and that's only there because when electricity was first discovered and current was first discovered in a wire, that's how they decided. And even though it was wrong, they stuck with it for long enough that that became the way that we say it is, and it's just the way we say it is now. So conventional current flows from positive to negative, but real current flows from negative to positive. All right, and that's it. We'll see you in class.